that aren't really there. So how can we tell when the patterns we find are really there? And I'm going to push this analogy on you of statistical inference and statistical physics. I hope it will be friendly enough so that you'll enjoy it even if you are not already acquainted with either of those things. So what is structure anyway? What does it mean to find something in data? So, you know, different fields have different attitudes about this. So it's interesting to philosophize about. It's, you know, 4 in the afternoon, we should philosophize a little bit. So, you know, one attitude is structure is what makes your data different from noise. So you have some structure-free model, a null model, which doesn't have any pattern in it. And if your data is really clearly not generated by that model, well, then it does have some pattern in it. Of course, what that null model is it's kind of a moving target, actually. So you might find something in your data which clearly disqualifies the really stupid model, but maybe it's something which you can easily accommodate in a new model, and then you want to see if your data is different from that new model, and so on. So you might make your null model more elaborate as you understand the data better. Another nice attitude is that you understand the structure of a data set if you can compress it. So, for instance, you have a marvelous network, and I say, hey, tell me the important stuff in this network, and I don't want you to just email me the entire network. That's the raw data. That would be very irritating. So I want you to tell me the important stuff. So I mean compress here in sort of different ways. One would be, I want you to send me a short version, like a gzipped version, which I can unpack on my end. And I could mean that I can get back exactly what the data was. Or I could mean it in some lossy sense about just tell me the important stuff. Of course, what's important is application dependent. So, and then another idea which is very popular in statistics and machine learning is that if you understand the data and I hide some of it from you, you ought to be able to fill in what I hid from you. And this is often called cross-validation or prediction. You know, if nature has hidden some of the data from you by dint of it not having happened yet, then you want to know if you can extend your knowledge of the data in some sense to what you haven't seen. Good. And there are some other ideas as well, but you know, there's a lot of pattern discovery. I found a pattern in this data. Well, what do you really mean? What is it good for? What is the, you know, can you now do something that you couldn't have done before, or do something more accurately than you could have done before? Okay, good. So I'm going to show you a really, really naive model of networks, which originated in the sociology community, and I think in the 1980s, and it's been rediscovered many times since then, well, without further ado. So it's called the stochastic block model. Some people write that as one word, but that would make it look like German, and so I put a space there. Okay, so here's the model. There are only k kinds of nodes in the world. People if it's a social network, species if it's a food web. We'll see a couple examples. And then there's a little k by k matrix. And if you want to know whether there is going to be a link between node I and node j, well, all you have to know is that I is of type R and j is of type S, and then there's a link from I to j with probability p sub rs. Okay, that's the whole model. So it says that the probability that you and I have a link between us depends only on my type and your type. And there's only k different types we could be. You can have a prior probability on the types if you want. For simplicity, I'm going to skip that for the most part. Now, but this matrix P could be fairly general. So for instance, it might not be symmetric. Predators eat prey and not the other way around. So I could have directed links. Also, we often assume that people are more likely to be friends with those similar to them. But there's a lot of networks where actually nodes are more likely to be linked to a node of a different type. Again, predators eat prey more than they eat other predators. So this matrix is not necessarily bigger on the diagonal than it is off the diagonal. So once I define this model, it's what we call a generative model. There are now a zillion different games we could play. So I could tell you this matrix P, and then I could show you the entire network, and I could tell you the types, the labels of some of the nodes, and ask you to try to label the other nodes. Or I could not tell you the matrix P, and I ask you to learn that from the data. I could hide some of the links from the network from you and ask you to guess what those missing links might be. I could add some additional spurious links that are false positives and ask you to try to do better than chance at flagging those as false positives, and so on. For most of this talk, we're going to play a particular game, which is I will not tell you any of the labels. I will show you the entire graph. I'll show you, for all pairs, whether they're linked or not, and then I'll ask you to find the labels. And that is, roughly speaking, called the community detection problem. So I just... And we know P? Let's say, for most of the talk, we'll know P. So I'm going to tell you, well, this is the probability with which nodes of different types connect. Here is the graph. Please clump the nodes of the graph into these groups. Label them according to which group they belong to. Good. So here are some examples. This is a fun network of political blogs from the 2004 election. I think Andrew Sullivan was one of the few that connected to both sides, if you know him. So these are the liberals and the conservatives, or maybe the other way around. Regrettably, people mostly link to others that they agree with. Here is a food web where down here are basic resources, here are plants, here are herbivores, up here are carnivores and things that eat those, or that maybe are parasites on those. That self-loop there is cannibalism, so, which is quite common, in fact. So here are the communities. You can imagine dividing this in many different ways. This is from a lake, but for instance, there could be the deep water part of the lake and the part near the surface or the part near the shore. So I could ask you to divide this geographically, or I could ask you to divide it according to trophic level, plants, herbivores, carnivores, and so on. So there's more than one kind of structure that we might be looking for here. This is a network of adjacent words in the novel David Copperfield, and the colors are whether they're adjectives or nouns. And in this case, or rather my student, told the algorithm that there were 3 types, and we didn't tell it anything else. And it kind of discovered on its own that adjectives in English tend to come before nouns, that nouns are not next to other nouns very often, except the phrase block model, where one of the nouns is actually acting as an adjective, but all right. And then it used the third group as a kind of catch-all for words that it had trouble classifying, like the word light, which appears in this text both as a noun and an adjective. So that's kind of fun. In this case, we had it learn the parameters. We did not tell it that adjectives come before nouns in English. Okay, good. So here are some matrices. I've kind of already said this, but this is the one we'll focus on mostly today. This is kind of everybody's favorite special case. Here there are 2 groups, and Republicans and Democrats say, and you connect to others within the same group with some constant probability C in, and others in the other group with some constant probability C out. But I'm going to divide both of these probabilities by n, because the hard case of this problem is when the network is actually quite sparse, when people don't have that many neighbors, and therefore it's a little bit tricky to figure things out about them. But just to show you some other cases, imagine a network where you have a densely connected core with a density of edges A, and then there's some lower density with which they connect to the peripheral nodes outside that, and perhaps some yet lower density with which those peripheral nodes connect to each other. So then the matrix would look like that. And then here's a version drawn straight from computer science where you are only allowed to connect to others of a different type from you. This is the graph coloring problem, where you're not allowed to, you have red, yellow, and blue nodes, and you're not allowed to have two nodes of the same color be connected to each other. So this is a completely, as we would say, heterophilic or a disassortative network, whereas this is, if Cin is bigger than Cout, this is more homophilic or assortative, where you want to be connected to others in your same group. All right, good. This was just a normalization factor there. Don't worry about it. Okay, good. So now we have this inference problem. Let's suppose I tell you this matrix, I show you the graph, I ask you to, well, come up with a good labeling of which nodes belong to which group. Well, this is NP hard. All right, let's go home. Yeah, so this is just saying that in the worst case, we think that this problem, doing this as well as possible, would be computationally hard. We think it takes exponential time. For instance, because it includes that graph coloring problem, which is one of the classic NP-complete problems. But this is really one of those situations where we don't care that it's NP hard in the worst case. Because what that means is that some crazy adversary could concoct a network which is really hard to classify into these groups. We're not in that setting. So we're in the setting where the network we're going to pretend was actually generated by this model. It actually has this number of groups. I just want to, parenthetically say, like, there's another problem which a lot of people struggle with, which is clustering points in n-dimensional space. And so this is a problem which is hard in the worst case, but why is it hard sometimes? Because there aren't actually clusters. So there's some beautiful recent work by Balkan, Bloom, and Gupta where they say, well, suppose there were actually clusters in a certain sense. Then under those circumstances, the best clustering or a pretty good clustering is not very hard to find. So I think this is often the case, when you are, inference is in some sense a kind of, you're going to have some optimization problem. Yes, a lot of optimization problems are hard, but if the thing you're trying to find is really there, it's usually not so hard to find. Okay, so that's, yeah, I'm not wearing my theorist hat today, but so anyway. All right, good. So there are a number of methods that work quite well in practice, and in some cases provably well if the network were actually generated by this model. I'll be telling you about belief propagation. There are kind of methods where we approximate the probability of a given labeling with a simpler function, which is easier to optimize. There are clever people who can just dive into the optimization problem and just solve it in practice using powerful numerical methods. There are some variants where there are these things called expectation maximization algorithms. There are spectral methods, which we'll talk about if we have time. But I really like belief propagation, not just because that was the one I was involved in, but also because it will build this analogy with physics, always a good thing to do. And it will also give us natural measures of whether what we've found is statistically significant, whether it's really there. And it will reveal phase transitions in when we can find it. So one of the themes you're going to see is that if your data set, in this case your network, is too sparse or too noisy, there can be a very sharp transition where when you cross that transition, you can no longer find patterns in it at all. So the phase transition I'm going to show you is, I think, actually somewhat generic in that you can expect it to show up, at least in a qualitative way, in a lot of other problems involving inference and big data. Okay, data, thou art so big. Okay, all right, so now let's talk a little bit about this analogy. There's gonna be some equations here, it'll be okay. So let's suppose that I fix a particular labeling of the nodes. So T sub I is which group node I belongs to. And let's just fix that. And then what's the probability of getting a graph, a particular set of edges? Well, by the definition of the model, this is a pretty simple function. It's just the product over all the edges that exist of the probability that they exist, and the product over all the edges that don't of the probability that they don't. So that's just telling you the model again in this format. Now, in physics, if you have something at thermal equilibrium, you know, rocks like to fall, so things prefer to be in lower energy states, but things are not at absolute zero, so there's always thermal noise jiggling them around, so that sometimes they're in higher energy states. And so the probability of being in a given state, according to Ludwig Boltzmann, is an exponentially decreasing function of the energy. So higher energy states are less likely, but how quickly this drops depends on the temperature. This beta here is one over the temperature. So for instance, at very low temperature, beta is really big, making this exponential very sharp, so that the system is really unwilling to be at any but its lowest energy states. At high temperature, beta is not so large, making this exponential more gentle, so that you're fairly likely to be even in high energy states. Well, let's pretend that, let's carry forward this analogy for a moment. I'm going to set the temperature to 1, so beta will just go away. So all I have to do to get the energy is minus the log, since the probability is supposed to be e to the minus energy. Well, okay, so far all I'm doing is rewriting things. The products turn into sums. And what this is a sum over all pairs of neighboring nodes of a little energy here which depends somehow on their types. So if you hang out with physicists or some machine learning people, you've heard of models like this. It's like the Ising model of, you know, iron atoms in a magnet, where neighboring atoms would like to have their magnetic fields pointed the same way. So they have a higher energy, meaning a lower probability if their spins disagree, and a lower energy or higher probability if they agree. And that's why, at least if the iron is not too hot, the whole thing lines up and becomes a magnet. Okay. There is also, there are interactions between the non-neighboring pairs. So for instance, you know, if David Mix-Barrington and I didn't know each other, well, you know, that would be weird, right? Since we've gone to some of the same conferences and have some interests in common, maybe one of us offended the other a while ago. So, the non-links are somewhat informative. On the other hand, if the network is sparse, so that the probability of a link is order 1 over n anyway, then this is fairly close to 1, its log is fairly close to 0. These terms are small. On the other hand, there are a lot of them. You can't totally ignore them. Anyway, but you don't have to think about them too much. So good, I already said that, I already said that. Okay, so now let me give you a nice two-way dictionary here. So the probability of you know, in a lot of inference problems, there are these hidden variables, which in this case are the labels of our nodes. The probability of your data set, given those hidden things you're trying to figure out, well, we'll call that, we'll just say that this is proportional to e to the minus 1 over the temperature times the energy, but the temperature is 1. Good. Minus the log of that, well, that's just the energy then. Low energy is high probability. Okay, well, what's the most likely labeling? The maximum a posteriori estimate. Okay. This is one of these fields where it is littered with 3-letter acronyms. I'm sorry, I can't do anything about it at this point. I would like to remove them all, but anyway. So this is the labeling which maximizes this probability of getting the data, assuming, I'm going to assume for the experts, I'm assuming for simplicity that there's a uniform prior. Well, physicists call this the ground state. It's the arrangement of the atoms or the labels or whatever that has the lowest energy. I will argue that this is actually not what we want to know. All right, what's the total probability of getting our network if we summed over all possible k to the n combinations of labelings? Well, that would be the sum of this little Boltzmann factor here, and that is called the partition function. and it is also how you normalize to get the posterior distribution. So the probability of the labels given the graph, well, it's proportional to the probability of the graph given the labels, but then we have to normalize. This is called the Gibbs distribution, and physicists call it the Gibbs distribution, or sometimes the Boltzmann distribution. So it's not that this analogy is totally new. It was already called the Gibbs distribution. But it's not just a normalization factor. It's a very important quantity. A lot of quantities we care about in physics can be written as derivatives of it. And it is also, in this case, a measure of the total probability of getting the network in the model. So I would argue it's a measure of how well overall the model fits the data. Minus its log is called the free energy. And one of the things I'll argue is that it's not actually the energy you want to minimize. That's this ground state. It's more to do with the free energy. Okay. All right, so anyway, your friend comes to you and says, right, thanks, but I have this network, and I got my article accepted to Science, and they told me that if I color the nodes of my network really nicely, I might get on the cover. So could you please tell me which nodes should be which colors? Find the communities for me. So, okay, let's say that we look for the best labeling. I mean, in computer science, our instinct is to say, oh, I know how to solve this problem. I mean, if we think there are two groups of equal size, and that you're more likely to connect to others within your group than with the other group, this is a problem we call min bisection. You know, just divide the network into two groups of n over 2 nodes each that minimizes the number of these unlikely between group edges. We know how to do that. All right. Well, actually, that's NP hard too, but let's suppose you could even do it. Well, I think you shouldn't, because this network doesn't actually have communities. It is a random 3 regular graph. That means every node has exactly 3 neighbors, but I wired them up to each other in a totally random way. But there are indeed ways to divide it into 2 groups so that only about 11% of the edges cross from one group to the other. Much less than half the edges, only 11%. So if I showed you this, you would say, thanks, Chris, you found the communities. Cover of Science, here we come. But the problem is, here's another one, which is equally good and has nothing in common with the one I showed you. Okay? So what's going on? We are overfitting. Okay? So there aren't actually communities here. And one of the ways we can tell there aren't actually communities is that there are many community structures that look good, but they're uncorrelated with each other. They don't agree. So there are many good fits, but they don't share anything in common. So, I mean, hopefully you've heard this kind of polemic before, but you don't always want the best fit to your data. So, for instance, even random graphs have things that look like communities, and, you know, humans were evolved to, you know, it's much better to think that there's a tiger there when there isn't than the reverse. So, but the problem is both we and our algorithms are good at finding black cats in dark rooms even when they're not there. So here are some stock prices. And I'm your financial advisor. And if you had been listening to me over the past 10 years, look how well my model fits these prices. It fits really well. Clearly, you should pay me a lot of money to tell you what stocks to buy, and then over the next 10 years, the data does that. And now, maybe I wasn't actually trying to deceive you. I was just getting too excited about the fact that this model fits the data perfectly. You don't want your model to fit the data perfectly, because if it does, you're probably giving your model too many parameters, you're making it too elaborate, and you're giving it the freedom to fit what is really only noise, as opposed to the true underlying structure. A much better model has fewer parameters. It's only a quadratic function instead of a 9th order polynomial or whatever that was. It doesn't fit perfectly, but it does a much better job at generalizing to what we haven't seen yet. So our statistician friends have been telling us this for a long time, but we don't always listen. I mean, a friend of mine who teaches probability likes to hand out at the beginning of his class a sequence of zeros and ones and ask the class to find the pattern. Of course, they find all sorts of patterns. And then he says, I flipped some coins. All right, so if finding the most likely labeling wasn't what we wanted, what do we want? So there's actually a theorem in Bayesian inference that by the way, I think I'm a moderate Bayesian. So there are, as you know, there are religious wars in statistics, and I don't actually want to be a casualty in these wars, but I think I'm an easygoing Bayesian. So turns out what you want to do is compute the marginal distribution for each node. What does that mean? It means for each node, what is the probability that it belongs to group 1 or 2 or 3? And then, if you want to label the nodes, you should assign each node its own most likely label, which is different from finding the overall labeling that maximizes that joint probability. Now, why should you do that? Well, it depends, of course. If I'm going to pay you $1 billion if you label every single node correctly, and nothing at all if you get even a single one wrong, then you want the ground state, or that maximum a posteriori estimate. But if I'm going to pay you $1 for each node you get right, then you want to do this. But the other way I like to think about this is, why would it be that, so what I'm saying is you have to sample the entire distribution of labelings, not just find the best one. You want to think about all of them, where each one is given a weight proportional to the probability that it would generate the data. So if in that entire distribution, a particular node is in group 1 90% of the time, what that means is that there are many good fits that agree with each other on the fact that node 1 that is in, what did I say? Group 1 is in that group. All right, so if you have these strong marginals, what it means is that there are a lot of solutions that agree with each other, as opposed to the thing I showed you where the different solutions were uncorrelated. So as a slogan you might want to walk out of here with, the consensus of many good fits is often better than the best single fit. All right, good. I think I'll skip over this, but let me just say that we're often trying to do model selection. So let's say, well, I'm not sure what kind of network this is. Maybe it was this assortative kind, maybe it was the core periphery kind, maybe it's disassortative. Also, a tricky model selection problem is how many groups are there, right? You have a real opportunity here to overfit, because the more groups you have to put the nodes in, the better the fit to the data it will look like you have, all the way until every node is in its own group of size 1. At which point, the matrix P is just the matrix of zeros and ones from the graph. You have fit the data perfectly and learned absolutely nothing about it, right? So, okay. So if you look at this total probability given a certain set of parameters, again, that's the sum over all possible labelings. Maximizing that is the same as, well, minimizing minus its log, which we call the free energy. And if you remember your first semester thermodynamics class, the free energy has these two terms. There's the energy, the average energy, but then there's the temperature here times the entropy. So minimizing the free energy means doing two things. You want fits with low energy, that means good high probability fits, but you also want the entropy to be large, which means you want many good fits. So here the slogan somehow is that a good model fits the data in many good ways. It's not just that there's one precise way it can fit the data, and that if you perturb it a little, it does poorly. All right, I guess I didn't skip that slide. Okay, but how are we going to compute these marginals and these free energies? Well, I think Monte Carlo is too slow. So what does Monte Carlo mean here? It would mean I would start with a particular labeling, it doesn't really matter, a random one, and then I would run around choosing a random node and considering flipping its label, changing it to a different group, and I would do that with probability based on the model, and I would run around and make these moves for long enough until I hopefully get so that I'm sampling this equilibrium distribution, the true posterior distribution of the labels given the graph. This is a very popular method in everything from computational physics to machine learning. For our purposes, it's too slow. We can argue about it if you want. Two reasons. One basic reason is that to compute these marginals, I need really good statistics about every node, so I would have to take many independent trials. Also, Monte Carlo, as John Makta here can tell you, is not so good at computing entropies and free energies unless you do something at many different temperatures. And anyway, never mind. So I'm going to show you something else. Belief propagation. So belief propagation is a really cute idea. It took me a long time to learn it. My friends tried to teach it to me several times unsuccessfully. The reason they were unsuccessful is as soon as they started writing things with double superscripts and double subscripts, I fell asleep. So, but if you've been wanting to learn it, it's actually really simple and nice. Here's the idea. So here are some nodes in the network, and we are going to try to estimate the marginals, but with a funny twist. So every node will send each of its neighbors an estimate of its marginal distribution. So I will tell J, I'm in group 1 with probability 40%, group 2 with probability 30%, et cetera. But there's the clever twist, first of all, is that I can send different estimates to different neighbors, and indeed it will. Moreover, when I figures out what it should tell J, it bases that on the messages it's receiving from all of its other neighbors. Meanwhile, it sends something to J based on all its neighbors other than, to K other than its neighbors, based on its neighbors other than K. So why is this? Well, two answers. One is that, let's suppose I go up to one of my fellow scientist friends and I say, hey, I've heard from a scientist that climate change is a hoax. And my friend says, hey, I just heard from a scientist that climate change is a hoax. And then I say, hey, I just heard that from another scientist. And it goes back and forth and just has this silly echo chamber amplifying this between us. We've all seen news shows like this. So the goal is to bring fresh information into the conversation from the rest of the network. That's one reason to base what I say to you based on what I hear from everybody else and not what I hear from you. There is a deeper reason, which I won't have time to go into, that finding these messages can be viewed as minimizing the free energy within a certain family of distributions, but I probably won't tell you that. Anyway, so what we do is we run around updating these messages, really just using Bayes' rule locally, until they reach a fixed point. Well, they might never reach a fixed point. It might never settle down. And if it does settle down, it might settle down to a terrible estimate of what the marginals are. But sometimes it works. All right, and in addition to the marginals, it turns out it also returns this quantity named after the physicist Hans Bethe, called the beta free energy, which is in many cases a good estimate of the true free energy. In fact, let's look at that beta free energy. Sorry. Let me just show you the update equation. It's not so bad. So again, this is what I tells J about the probability that I belongs to group S. That's our notation here. This is just a normalization factor. That's the prior probability of being in group S, which I told you that wasn't going to matter anyway. But if you thought that there are more people in group S than in some other group, you can put that here. All right, now the real meat of it. I take the product over all my neighbors, other than you, the one I'm talking to, and then I look at the messages they're sending me. If one of my neighbors says that she is in group R, then I will put a weight here because we are neighbors equal to the probability that there's an edge between us, or that there would be if indeed she was in group R and I was in group S. This is just Bayes' rule. It's really just Bayes' rule. We're just using the information that there is a link between us. This, in this particular model, we also have these messages between the non-neighbors. That's kind of too many messages. But anyway, there's something more important to tell you about, which is that By treating this as a product over my neighbors, I'm making a huge assumption. I'm assuming that conditioned on my state, my neighbors are independent of each other. To put it differently, I'm assuming that my neighbors are only correlated through me. Now, of course, if there's a loop that goes around in the graph and connects them, well, but maybe it's still okay because, you know, the correlations could decay with distance and that loop will typically be long, so they're nearly independent. But come on, give me a break. People introduce their friends to each other all the time. So in a lot of real networks, there are a ton of triangles, in which case they're directly connected. So where do I get off saying that they're independent? Well, it still often works pretty well in practice. You know, understanding how badly this assumption gets our, you know, how badly it damages our estimates is an active field of research. But one thing I can tell you, well, I'll tell it to you as a warning label, this is exact only on trees. So if the network were really a tree, this would be fine. Except for these things, don't worry about them. Of course, hardly any real network is a tree, so all right, well, but let's try it anyway and see how well it does. So because everybody's talking to everybody else, both your neighbors and your non-neighbors, that's n squared time, and I know that's still polynomial, but n is 1,000,000, so n squared is too big. So the next thing we do, which I won't go into detail, is we treat all of these non-neighbor messages, since they're kind of not that strong anyway, we kind of wrap them up into a simpler term. Now we only have a number of messages to pass around, which is equal to essentially the number of edges in the network, or twice that because they go in both directions. And now this is, I'll call it scalable. Scalable, of course, is partly in the eye of the beholder, but now, you know, linear in the number of links in the network seems like that's attractive. Now that's per iteration. It may take a long time for this to settle down to a fixed point. Good. So let's talk about this network. How many of you have already heard of this network? Okay, it is the hydrogen atom, the Drosophila, the nematode of this field. Briefly, there was a karate club at a university. There was a anthropology graduate student named W.W. Zachary. I believe I accuse him of fomenting an argument, but you know, it was time to publish his research. I believe he fomented an argument between the president and the instructor of the club. I don't know how he did it. I know I'm making this part up. But anyway, they had a fight, and then it divided into two factions. So then a favorite pastime is, you know, based on who hung out with whom outside the meetings of the club, the social network, can we correctly retrodict how it would divide into these two factions? Zachary, in his thesis, used the max-flow min-cut algorithm, and it worked just fine. You know, if your algorithm doesn't work on this network, which only has 33 nodes, then you should go home. However, I will mention there was one node his algorithm got wrong, which was a node which was good friends with the president, but stuck with the instructor because he had a black belt exam coming up in a couple of weeks, and he didn't want to start over with a new instructor. So we should keep in mind that these digital data sets always leave out a lot of real-world information. Anyway, if you ask the block model what it thinks about this, you say there are two types of nodes, find them. It often says, I found the two kinds of nodes. See, there are these high-degree central nodes that are connected to a lot of people, and then there are these low-degree peripheral nodes. Did I get it right? And, well, kind of what we wanted was these two factions, but it's not wrong. It just found some other way to divide it into two groups. Well, one thing we can do is compute the free energy. And we can sort of scan through the parameter space interpolating from this core periphery picture to the two factions, and we can observe that indeed both of these are local optima in the free energy, which is kind of nice. So we can look at the landscape of possible models. Okay, anyway, belief propagation is an algorithm. It's pretty fast. You can run it on real networks. I claim it's competitive with other people's algorithms for community structure. But it also lets us do some theory. So it lets us compute some analytic things about how well we can find communities in networks, at least, if you'll be generous to me, networks generated by this model, where I can really prove things about it. We can argue about whether this will hold for real networks, but anyway. So what we're going to do is think about the fixed points of the messages and when they're stable, and you'll see what happens in a moment. So first of all, this is the convergence time. There are red and green things here. I'm not sure if you can see them. This x-axis is a measure of how strong the community structure is. It's the ratio between the probability of connecting to someone outside your group versus inside your group. At this end, you only connect to others in your group, so the structure is very strong. At this end, it's actually a completely random graph. If you're familiar with Erdős-Rényi random graphs, everybody is equally likely to be connected to everybody else. Well, the good news is that the red and green things are for two network sizes of 10,000 and 100,000 nodes, and the y-axis here is just the number of times we needed to iterate before reaching a fixed point, and it doesn't seem to depend very much on the size. You can prove it does have to depend logarithmically on the size. But the other thing you notice is that it explodes at a certain value of this ratio. What's going on? Well, to a physicist, this is a sign of a phase transition. Everything gets slower as you get close to a phase transition because there are bigger fluctuations and it takes longer for things to settle down. You have longer range correlations, both in space and time, and that makes it harder to reach equilibrium. So, same x-axis, strong community structure here, none at all there. Now the y-axis is the accuracy we achieve. The fraction of nodes that are labeled correctly, where 0 here means no chance. I just flipped a bunch of coins. And what's interesting is that, well, yes, we do really well when there's a lot of structure. I expected this to just go continuously to 0 as there was less and less structure, but that's not what happens. What happens is that even here, say, where you are twice as likely to connect to others in your group as opposed to outside your group, we do no better than chance. And I think this was a little gutsy, but my co-authors insisted on conjecturing in this physics paper that no algorithm can do better than chance. That this is not just a fact about belief propagation. And I said, wait, you mean it takes exponential time? And they said, no, even given exponential time, that the information isn't there. I was like, okay, all right. So, well, indeed, there is this undetectable region for two groups. Here is the precise location of this threshold. The difference between connecting in and connecting out has to be 2 times, this is the average degree, the total average number of neighbors you have. And this 2 is really a 2, it's a precise constant. Why? What's going on? Well, there is a stupid fixed point that belief propagation can fall into. At least in a symmetric case where the groups are of equal size, I could say, suppose that all of my friends tell me that they're equally likely to vote for any of the 43 candidates in the primary. And then I think about the fact that I respect all these people's opinion, I carefully do a calculation, and I report that, I am also equally likely to vote for any of the 43 candidates. So there is a fixed point where all of the messages are uniform. Everybody says I'm equally likely to be in every group. The question is that fixed point stable? Well, what happens is that this is the point, the transition at which that fixed point becomes stable. So in this regime, and it turns out there are subtleties here, but for two groups, it turns out it's globally stable. So if you start out with arbitrary initial messages, belief propagation will get sucked into this fixed point where everybody's equally likely to have every label. On the other hand, in this regime, this trivial fixed point is unstable. Even if you perturb things slightly, you fly away from it, drawing stronger conclusions about the nodes, and happily you fly towards the truth and achieve a high accuracy. So one of the nice things about this interdisciplinary business is that I get to publish things whether or not I can prove them. So if I can't prove them, I publish them in physics. And if I can prove them, I publish them in math and computer science. So we said this. You know, we didn't say we conjectured, we said we show, because it was a physics journal. Anyway, then these people proved it in the case of two groups of equal size. For more than two groups, it turns out to be much trickier, partly because something genuinely different happens. So I should mention that these guys, Elchanan Mosel, Joe Neiman, and Alan Sly, showed that in this regime, it's really information theoretically impossible to find the communities. It's not a matter of computational complexity. In fact, they showed that you can't even tell whether the graph was generated by the block model with communities or whether it was a purely random graph with the same average degree. You cannot with certainty distinguish which of those things I did. So you can't even tell that there are communities, let alone find them. That's a cool result. For more groups, more stuff happens. So here, there is an intermediate regime. This is actually this thing called the planted 5-coloring problem, so I'm not sure I want to go into details. But let me just say that in this regime, belief propagation has two competing fixed points, indeed sometimes more than that. Here's the trivial fixed point, which is no better than chance. It is locally stable, but it's not globally stable. There is another fixed point which is quite accurate, which is also locally stable. The problem is that it has a very small basin of attraction, meaning that unless you start out quite close to it, you will instead slide into the trivial one, which collects almost all initial guesses about the messages. Everything I just said is totally non-rigorous. So if you're a theorem prover, drop everything else and start working on this. So the point is, you need a lot of help. You need a strong initial hint in this regime to find that accurate fixed point. So what we say is that in this regime, finding the community structure is information theoretically possible, but we think it's exponentially hard. That you would really have to scan the entire space of messages or do many, many independent runs to find that good fixed point. Well, if you need some help, I'll give you some help. I'm going to tell you the true labels of a certain fraction of the nodes. I'll just tell you that for free. What happens? So can you extend from the known nodes to the unknown nodes what their labels are? Well, some nice things happen. So this is the density of the network. This is the fraction of labels that I told you for free. What you see here is that there's a line of discontinuities where if I push the fraction of nodes I tell you beyond a certain point, suddenly your accuracy jumps. Roughly speaking, because I got you close enough to the good fixed point. I think of this as a little bit like percolation, where if I tell you only a tiny fraction of nodes, well, you know them, because I told you. You know their neighbors better than chance. Maybe you can do a little bit better than chance on their next nearest neighbors, but that it decays rapidly. But that if the number of known nodes I give you is above a certain threshold, then your information percolates to the entire network and you do well. So that's another nice phenomenon which we cannot prove rigorously. Let me mention one other setting. As you can see, we're starting to churn out too many papers, and maybe it's time to switch topics, but here's another paper. So let's have a dynamic network. Most networks are. They're changing in time. So here what's going on is that with a certain probability, which is this axis, from one time step to the next, the node stays in the same group it's in now. With 1 minus that probability, it chooses a new random group. Okay? So if you never stay, well, if you don't retain your label from one step to the next, if it's random every time, then each snapshot is a completely separate network. So we just have to treat each snapshot separately. And then the threshold is where it was before. As you increase the correlation from one time step to the next, the probability that I will retain my label instead of choosing a new one, then we can find more, and we can detect weaker and weaker structure because you can add up information over many time slices and integrate that and do better. And we can compute this curve, and it looks like it fits with experiment. All right, so we can add more data. Things are not just graphs. I'll just click through this, I'm sorry. So suppose your network is a network of documents. So some of you know about clustering documents based on their words. So let's have both the words and the links between them. So for instance, patents, like scientific papers, cite other patents. So let's use both kinds of information, the words in the documents and the topology. And so we tried this out in a bunch of microprocessor patents, and it finds groups that seem to have something to do with the microprogramming and the instructions, testing and debugging, the power supply, encryption and security, and the program control. That's kind of nice. And that was with Lisa Couture, who some of you know. Okay. In my rapidly decreasing time, let me just say a little bit more about the statistical significance business. So this lets us now play with the temperature a little bit. Before, the temperature was 1 everywhere. Now I'm going to play with the temperature a little bit. So remember that if I go to lower temperature, I make this exponential steeper, and I'm focusing more on the really low energy things. So as I push the temperature down, it's like I'm demanding more structure. I'm looking harder for patterns. I'm pushing towards the ground state, the most likely labeling. So at lower temperatures, I'm being greedier and assuming that there's more structure in the data. Well, what happens if I look for more than is really there? How does the physics respond to that unreasonable demand? So what will happen, I claim, is we'll get lots and lots of near optima. We'll be jumping around between them, but they'll have nothing in common, like I said. And what actually happens is that belief propagation goes on strike. It stops settling down, and it enters what we call a spin glass phase, where it just jumps from place to place in this very bumpy landscape. Roughly speaking, it's jumping from one local optimum to another, and never really choosing a nice region of the state space where we'd get some agreement. Good, so let me just show you an example of this. There's a quantity that a lot of people in network science like, called the modularity. It's just the number of groups, the number of edges within groups minus the number we would expect if the network were randomly rewired. The problem is that even random graphs can have a high modularity. So here are 2 graphs. I have arranged, these are adjacency matrices where each row in each column is a vertex, and there is a dot if there's a link between them, and which one really has communities. This one has, this community structure has a modularity of 0.39. This one has a modularity of only 0.33. Well, guess what? This is a completely random graph. So this is like the example I showed you before with the red and blue nodes, where out of all the ways to divide it into 2 groups, there's one which looks pretty convincing. This is the true labeling of a network that I made with the stochastic block model deep in the detectable regime. So this is the true community structure, and it has a lower modularity than the fictional community structure of this other graph. Okay, all right, so we should watch out for this. So what happens? At low temperature, at really high temperature, which means low beta, the modularity you find is 0. So this is, again, this trivial fixed point. Everybody's equally likely to be in every group. You say, no, find me structure. I demand it. I push the temperature down, which means pushing beta up. And finally, the algorithm says, okay, I found some high modularity structures, but it jumps all around between them. It doesn't converge. And if I ran the algorithm again, it would find totally different ones. So, you know, it's under duress, this algorithm. On the other hand, if there is real structure, there is a nice middle ground where it settles down, it finds high modularity things, but these all agree with each other. And that's sort of a sign of I would argue, statistically significant structure. What's going on in terms of the energy landscape is that this one is just very bumpy with lots of local optima. This one has a nice big peak around the true structure. And so we settle down there, sample these nice places up there, and they all agree with each other. Okay, oh, and then another thing you can do is keep subdividing. I can't skip this, it's too pretty. You know, you can keep subdividing the communities into subcommunities until this method tells you that there's no statistically significant structure any farther down. And at that point, you can stop. This is the blog network again. Let's say these are the Democrats and those are the Republicans. And it looks as if there are lots of subcommunities here. I would like to say that these are the labor Democrats, and these are the environmentalists, and those are the anti-abortion Republicans, and those are the capitalists. And unfortunately, it's very sad, but all the thoughtful comments and posts by all these blog writers appear to be lost in the mists of time. So I cannot go back and validate for you this claim about the structure, but it looks convincing. Okay, all right. So I'm going to skip what I was going to say about spectral methods. It's really cool, and there's a lovely picture here. You know, you always have too many slides, even when you know that you always have too many slides. I will just show you the spectrum in the complex plane of this linear operator, and I will show you this one, which looks like, since we just had Halloween, and that looks a lot like the Eye of Sauron tilted on its side. But the idea is that this eigenvalue in the complex plane corresponds to the true community structure. As we weaken the structure, at a certain point, it crosses into this disk and becomes lost in a sea of uninformative eigenvectors, and that happens exactly at the detectability transition. So I will skip all that and end with my morals. So the most likely model often overfits. And even if you could find the best fit, which might be NP hard, you don't want to. What you want is to understand something about the entire distribution and whether there's some strong consensus in it. Belief propagation is one way to do this, and it works quite quickly. It certainly makes some assumptions which may or may not hold in real data, but it also lets us find analytically where these phase transitions are, and the spectral algorithm I showed you we got by taking its derivatives, just linearizing it around that trivial fixed point and asking whether it was stable or not. And finally, whether the landscape of possible fits is smooth or glassy and bumpy is a heuristic, at least for whether what we found is really there. Since a lot of you are machine learning people, I just wanted to comment on this because I consider myself a computer scientist, but I was raised as a physicist, and I still have certain physics attitudes. For instance, it is much better to say something false than to say nothing at all. You should teach all your students that. But also, physicists like things to be simple, you know, so a lot of people in machine learning, they're like, well, the data is rich and complicated. Our model of the data must be rich and complicated. In order to fit this rich, complicated model, this rich, complicated data, I will use powerful techniques. And it's great. It's fantastic. It's just that I guess I'm coming more from a theory side, so I would rather take a simple model, which in many ways is quite naive, but understand really, really well what its strengths and weaknesses are, and when it works and when it doesn't. And I will also say on a practical level that sometimes the simple models, because they're easy to work with, they might be faster and they might actually do better in practice. And that has happened occasionally, like in our paper about text document networks. So I think that when things are elegant and tractable, I would argue that this sometimes even pays off when dealing with real data, because the simpler models can be easier and faster to optimize. This is not always going to work. But also, I know something about the model. So when I read a machine learning paper, and it got an accuracy of 87%, and last year's algorithm only got an accuracy of 82%, And the new paper had 6 new ideas in it. You know, it changed the model in this way, and it also souped up how it fits it, and it did this other cool thing as an outer loop, and it tuned the parameter that way instead of this way. It's like, well, great, but I don't have a clear sense of which of these techniques is really behind its strength. Why did it do better? And on what kinds of data sets will it do better? So for me, these simple models are attractive for that reason. In the 19th century, everything was a steam engine. Then, in the middle of the 20th century, everything was a computer. In the 90s, briefly, everything was an economy, even the brain, unless you were a little bit greener, and they said, no, things are symbiotic, everything's an ecology. And now everything is a network. So each of these metaphors helps us see certain things about the real world more clearly, makes it harder to see certain other things. These metaphors need to pay their own way, and we should take everyone with a grain of salt. Buy my book. Thank you. Yes?
This is an awfully specific question, but one that I would love an answer to.
Okay.
So when you have a graph model and you make predictions using the maximum marginals, you tend to do better if you're just trying to label the individual, but it's not important that you distribute, right?
Right.
However, when you're training it, if you're using beta-free energy, that's approximation to the actual joint distribution.
Well, it's a measure of a sum over the entire joint distribution.
What I'm wondering is, would it be better to use some measure over the marginals, which I guess this is, but it's a very specific one that's supposed to approximate that use for the joint distribution rather than the beta-free energy itself?
Okay, so what belief propagation tries to do is it tries to find the one-point marginals, the probability of, I know you know a lot of what I'm saying now, but for everybody. So in essence, it is trying to do as good a job as possible at approximating the true posterior distribution, which is all kinds of complicated joint correlations. It's finding the closest possible distribution. Literally, it's minimizing the Kullback-Leibler divergence, which turns out to be the same as minimizing the free energy, within a family of distributions that only pay attention to the 1- and 2-point marginals. So only the marginals about single nodes and the pairwise correlations between neighboring nodes. So it works to the extent that higher order correlations don't matter, and in particular that your neighbors are not correlated with each other except through you. There are caveats to what I'm saying, but let's not worry about them. So if you were training the model, then I would argue that this is the thing to do, because you are, well, I think the idea of minimizing the Kullback-Leibler divergence between this sort of belief propagation approximation to the posterior distribution and the true posterior, that seems like a really good idea. Now, I'm not sure, again, it depends on your loss function, right? It depends on what you're trying to optimize. And I admit that you didn't say the loss function was the divergence. Maybe it's the fraction of things minimized. So maybe it's not exactly the right thing to do. I'm not sure. Yeah. Okay. Yeah.
So in the machine learning community, there was a phase that people went through that they mostly abandoned, where they're really excited about convex approximations of the data free energy.
Oh, yeah, uh-huh.
Because we were really scared of non-convex optimization. But it turns out that's not a particularly good approximation. But it's still sort of easier to study because there's only a global optimum. And so how can you leverage those convex approximations to convince an output?
I am trying to learn more about that now. And of course, so let me give 2 answers. One is what you probably already know. So in fact, the pseudo-likelihood thing I mentioned by Arashamini and Liza Lavina and Bickel and Chen, I think. So that is a kind of convex approximation to the likelihood. It's also true that, you know, the block model, in a sense, is finding a type of low-rank approximation to the adjacency matrix. Because if I tell you that, roughly speaking, there are 3 blocks of vertices, And within these blocks, you have one density of edges, and outside them off the diagonal, you have another density. That's a rank 3 approximation. And then, so there's this whole world of low-rank approximations to matrices and tensors, and convex relaxations are a major tool in this world. And so I'm trying to catch up on all that work. But the other thing I would say is, I think it's cool that belief propagation isn't convex. I think that's a feature and not a bug. Because it's really cool, for instance, in the case I showed you with the 2 competing fixed points, there really are 2 fixed points of belief propagation that correspond to 2 regions or clusters of fits. One of which is, the trivial fixed point, which corresponds to fits that are uncorrelated with the ground truth. And the other is this accurate one, which is much more correlated with the ground truth. And I think it's instructive that they're both there. There are further transitions that I didn't tell you about. So for instance, as you make the community structure weaker, the beta free energy of the accurate one becomes larger, that is not as good, as the trivial one. And at that point, a Bayesian would say, oh, well, even if you show me this fixed point, I don't believe it. Because most of the posterior distribution is over here. And so at that point, other things happen. There are many other fixed points that show up as well that also, that none of which, so all of which look just as good as the accurate one. So I think these transitions are interesting, and we would miss them if we took a convex bound on the whole thing. We would miss this information about these multiple fixed points. I think they have something to say to us, that the algorithm can get stuck here or it can find that over there. So